Okay, so the first thing I want to, so last time in concluding I stated a theorem for which I'm going to give the proof now, which was a theorem on the space of paths. So first I told you that there are three definitions of globally hyperbolic, and the three definitions, I wrote them down again last time, but let me anyway just summarize them very fast because you might have forgotten. So definitions of global, I don't know if this is readable actually, this chalk is a bit strange. Somehow the dustful chalks wrote better than the dust-free chalks. Yeah. So this time I won't write them down in sentences, I'll just write the summary. CPQ compact, since I'm going to state what is CPQ, it's just the state of causal, space of causal curves from P to Q, and the definition is due to Leray, and historically it was the first one, I think. The second is there exists a Cauchy hypersurface. That's really all you need to say, because by definition of Cauchy hypersurface, all inextendable causal curves have to pass through it, and we call this Gay-Roche's definition. And the third one was that the causal diamond DPQ is compact. And just to remind you, if I have P a point in the past of Q, then this thing, dpq, by definition, is J plus of the point in the past intersection J minus of the point in the future. And the picture is like this. Here is P, here is Q. So J minus of Q looks like that, including everything. I mean, its boundary also, because causal curves. And J plus of P looks like that. And so this is the diamond, and that is dpq. So that's the space which we are saying is compact. And these are all supposed to be equivalent, but this one we have picked as our definition, and therefore, as I mentioned last time, you have to prove that this implies both of these and any of them implies the other two. So we are not going to do all the proofs, but we'll certainly do some of them. Okay, so last time we discussed why, so we stated the theorem, and now today we need to prove it. The theorem says, okay, last time we also defined a topology. We defined a topology on CPQ, otherwise the statement that something is compact makes no sense. So the topology was defined by saying that this is P, this is Q. Whenever you have an open set that of the manifold which encloses both of them, then the open set in the space of curves is all causal curves which lie in this open set. Okay, so U of O we call all causal curves fully contained in O. Obviously they start and end in O by definition. So note that it's not that all causal curves from P to Q need to be contained in any O, because O you can choose how, M has a lot of open sets. I could even be very mean and choose my open set like this, and that would rule out a lot of curves which are perfectly causal, but which just don't happen to fully lie in this. Okay, so but the point is that those which do lie in it for any open set O are the ones which define the open set U of O. That's an open set on the space of causal curves. Okay, good. The last thing that I need to state from last time Okay, before that, then let's state the theorem now. With this topology, CPQ is compact. I don't need to write it again, it's on the board. And we need to prove it. Then last time we also discussed how we can't really prove something is compact very easily if the space is very complicated, which is certainly true of the space of curves. So we use the fact that compactness of any space is equivalent to sequential compactness. We'll use this repeatedly today. I didn't highlight its role last time, maybe, but today we'll certainly use it. Plus second countability. The second countability is that there exists a basis for the topology we are working with, which is countable, and because the manifold has a basis of open sets O, which is countable, which are the balls with rational radius, and these are inherited from those. Therefore, because for every O we get a U. So if we have labeled all the O's by some, counted them and listed some integers which label them, then we have done the same for U. So it's certainly second countable. This is the trivial part, and this is the one we have to worry about. Now sequential compactness, so this statement that compact and sequential compact are the same, this is a theorem in topology which I won't prove. So generally if there's a theorem in somewhat sort of basic topology, I won't prove it, but anytime you want, I can always give you some kind of intuitive idea why it should be there. And you can also ask me after the class or any other time, or now if you like. Okay. So compact, by the way, means every open cover has a finite subcover. Okay, and sequentially compact means. Let me see that, because now I'm a bit scared to write down theorems without checking the exact wording. Yeah. So sequential compactness means every infinite sequence has a subsequence that converges. To a limit. That is in the set. So of course, what can happen, and it typically happens for non-compact sets, is that you can have an infinite sequence which converges to a point which isn't in that set. I showed you an example. If you have forgotten, is the example of an open interval. So open interval 0 to 1 is compact, and you can find a sequence of points starting at 0, then going to half, 2/3, 3/4, 5, 6, It's an infinite sequence. The sequence is given by an equals n upon n plus 1 for integers n. So as n goes to infinity, you can see that an goes to 1, but 1 is not in this open interval, because exactly open interval means that we only consider points such that 0 strictly less than x, strictly less than 1. Okay, and this sequence doesn't have any point in the sequence which is actually equal to 1. There is no an which is equal to 1. But in the limiting sense, it limits to 1. It converges actually to 1. And that point by lying outside tells us that this open interval is not closed. Okay, good. So we use these kind of things. And now we are going to talk, okay, so now we have to talk about this subsequence business. This is the point which is a little extra complication, and I'll try to explain why we need to talk about a subsequence, but actually it's exactly what Omkar asked about last time. So the point here is anytime you say every sequence converges to a limit, you are putting yourself in trouble because there could be sequences which just keep running around without ever converging. And the classic example is an equals minus 1 to the n. This is an infinite sequence and going from 1 to infinity. And it simply takes two values. It's a sequence of real numbers. So I can plot the values of it. And these are the only values it takes. But it refuses to settle down either at 1 or minus 1. So limit n goes to infinity of an does not exist. It's not a convergent sequence. Okay. So this sequence has no convergence point. Convergence point by definition is a point such that all members of the sequence for large enough n are arbitrarily close to that point, and it doesn't have that. Okay. However, it has, so this is one fact, but it has accumulation or limit points. They're called accumulation. I like that word, accumulation points, but just to follow the literature, I'm going to use limit points. This is a limit point because the limit point is defined for a set by exactly this subsequence. That means for a limit point to be there, there must be an infinite subsequence of this sequence which is arbitrarily close to 1. Okay, and what is that subsequence of this? It's the subsequence of all even numbers where all the terms are 1, so obviously it converges to 1. So convergence is stronger, you want the whole sequence to converge. But some nasty person gives you a sequence which doesn't converge, you should be clever enough to see if there is a subsequence which does converge. And if so, we say that it converges to a limit point, but which limit point would depend on which subsequence. And in this case, the even subsequence converges to one limit point and the odd subsequence converges to another. Okay, so we'll use the language that such a series has a limit point, in fact has two, even though it doesn't have a limit. Now this is a little unpleasant use, double use of the word limit. The problem is that I guess sequences were something older and people used limit to be the convergence, the point to which it converges. So if you look at the Wikipedia entry, they say care must be taken not to confuse limit of a sequence, by which they mean that, and limit point of a set. Okay, so they would actually, Wikipedia would not, whoever wrote that, would not like me to call this limit points. Since it's a sequence, I should either use convergence point or accumulation point. Okay, but Wald is my boss, not Wikipedia, and he uses limit point for this thing, where there's the subsequence which converges, and convergence point when the actual sequence fully converges. Okay, it is certainly a very picky mathematical subtlety, but you will see that, well, actually, as I said, there was already a question on it, and you will see why it's quite essential. So the first thing is, in sequential compactness, every infinite sequence has a subsequence that converges to a limit. That's the same as saying every infinite sequence has a limit point, at least one limit point. So I can actually, in view of the discussion on the right side, I can just give the definition as of sequential compactnesses as every infinite sequence has a limit point. Just we keep in mind, maybe more than one. That we don't care. Could have more than one limit point. You could have easily rig up a sequence which oscillates between three numbers, then it has three limit points. Okay. Now we finally okay. So let's conclude this. So if we have a closed set then every infinite sequence. So a closed set is one for which this is of course the original definition, for which every sequence has a limit point in that set. This is the definition of closed. And now you can see that it doesn't mean that every sequence in a closed set converges to the limit point. It means the weaker thing. It's not necessarily a convergence point. And we need this because otherwise our theorems won't be true, because our theorems you can make a broad claim that instead of this, I say a closed set is one for which every sequence has a convergence point. Then the problem is nothing is ever closed, because I can always pick a sequence which oscillates back and forth between some 2 points, and it will never have a convergence point, and so it's an empty definition. So you see, what looked very picky, that take a sequence and allow for a subsequence, is not picky, it's actually very crucial, otherwise you don't have a definition of closed at all. And if you don't have closed, you can't do sequentially compact either. So because that we'll use the closedness to do that. Yes.
But I thought closed just meant complement of open.
Yeah. So that's okay. So there are two in a topological space you can have two definitions of closed which are equivalent. One is closed set is the complement of an open set, and the other, which actually in some sense is the basic one. Then this is a theorem that if you have a set which is a complement of an open set, then every sequence has a limit point in the set. But again, limit point, not limit. Okay. Now with that, the strategy to prove our theorem requires few definitions about the space of curves, because we are trying to prove theorems about the space of curves. So now it will become much easier to understand what is the convergence point or a limit point of a family of curves. So we'll call this family x and mu of lambda. And right now we don't have to care too much whether these curves begin or end somewhere or not. We'll just take any kind of curves and just define convergence point and limit point for curves. But we'll see there's one cute subtlety. So a convergence point for a family of curves okay, we'll say P is a convergence point if for every O, I'm always going to use this O for open set. So if I don't write it, you should generally assume that if every O which contains P, so that's O, the curve x and mu of lambda intersects O for n greater than n. Again, this is a calculus thing. I should finish the sentence by saying there exists some integer capital N such that this is true, but I think you just should understand it. For small n, sufficiently large is what we are saying. That means somebody gives me an O, I will find a capital N such that all the curves from the capital Nth curve onwards all intersect this thing. So you can see clearly that this is convergence point. Okay, so if your family of curves happens to be the kind which only has two values like that, there are only two curves, and for n odd you are on one curve and n even you are on the other curve, then of course it won't have a convergence point. So what are we going to do? We also have to define a limit point, because that's the thing that we work with. I'm sorry, I know everybody here, including myself, didn't sign up to be a mathematician, but it's actually not very difficult once you get the hang of these ideas, and actually they are very, I would call them very satisfying, because at least now you know what you're dealing with somewhat on a somewhat rigorous level. Okay, so when should I call a point P a limit point of a family of curves? I think by now you know enough to tell me the answer.
You can choose a
Subsequence which intersects any O. So P is a limit point of X and mu if there exists a subsequence. This is the simplest or fastest way to say it, for which P is a convergence. You just recycle that definition, but if somebody has given you a family of curves, you just have to pick an infinite subsequence. So the subsequence still has to go all the way, n has to go to infinity, and it just has to be a convergence point as per this definition. So now, if your family of curves had only two curves, let's say n odd and n even, then if P lies on one of these curves, it's a limit point of the family. Also, if it lies on the other one, since they don't do anything except oscillate in this weird example, any P which lies off both of them isn't a limit point or a convergence point or nothing. So it's all extremely clear. Okay, now the cleverness, and I'm really not completely sure who to. I think Gerosh is the first one who did these things. I could be wrong. The cleverness is now to try and ask what is a convergence curve. So I'll just cheat and write it here. It's a convergence curve for a family X and mu if for every, so now remember we have a topology on the space of curves, so we are going to use that. So but we can actually do it more simply if every point on X mu. So X mu is a distinguished curve. It need not be any member of this family, but it's a definite curve, so it's made up of points. And it's a convergence curve if every point on X mu of lambda is a convergence point. Okay. Now this is relatively straightforward, because what do we want? We want this family of curves to get closer and closer and eventually come arbitrarily close to the yellow curve. Okay. But in the process of this coming arbitrarily close to this whole curve, it comes arbitrarily close to every point of this curve. So any point of this curve, if I surround it by an open set O, then as you can see, all the sufficiently high members of this family intersect that point. So it's a very natural definition that a convergence curve is for a family, X mu is a convergence curve if every point on the hypothetical convergence curve is a convergence point of the family. This one is easy. But defining the limit point is tricky. So the first inclination would be to say that X mu of lambda is a limit curve. This is what we want to define. If every point on it, the family is always X and mu, on it is a limit point of the X and mu. So, question mark, is this a sensible definition? It's a beautiful exercise. If you stare at it, you will see that it isn't the right definition.
Go like one curve, one curve, one curve.
Exactly. What I think you're saying is the following. You see, for every point to be a limit point, for each point there should be a subfamily of this curve which converges to that point. But it could be a different subfamily that converges to different points on this curve. Then you can't very well say that the curve is a limit curve. We want a curve that at least one subfamily of this set of curves hugs that curve, the whole curve. But instead, if we give that definition, which is wrong, I'm mentioning it precisely because it's wrong, then we would say, okay, this point is a limit point, so some of these curves converge to it. This point is also a limit point, but other set of the original curves converge to it. I can pick any infinite subsequence. Okay, so for example, I could say in my family of curves which oscillate between two values, one limit point would be on one curve, one limit would be on the other curve. Together they don't make a they don't make a limit curve, they don't make a curve at all. So it would not be a good definition, and so the correct definition is not this, but instead, and it's immediately obvious to see why, if there exists a subsequence of x and mu for which it is a convergence curve. So you pick the subsequence once and for all of your original family of curves. Okay. Now that subsequence, as we always saw, when you pick a subsequence, it's supposed to converge, not just have a limit point. So we pick the subsequence once and for all, one subsequence, not one for every point along the curve. And now that whole subsequence is supposed to end up getting very, very close to this yellow curve, then it's a limit curve. So now finally we have defined limit curve correctly, and this is what we were after. The problem is we can't define limit curve by only defining limit point. We have to define convergence point, convergence curve, and then limit curve. We could have maybe skipped talking about limit point because actually limit point is not used here, but the idea is used here. And this is a very, it's very obvious that this subtlety comes from the fact that we are talking of curves which have many points rather than doing point set topology. In a way, these are some curve space of curves topology, which from the geometric point of view is infinite dimensional, because in given 2 points, I have infinitely many curves, and you have to parameterize them by deformation of all the points along it. It's a bit like string theory actually. Okay, good. Okay, now now we are set with the definitions. Now a lemma and then the proof that CPQ is compact. Are there any questions? Please feel free to ask questions. That's what this class is for. Anything whatsoever.
Sir,
Yes.
can you please go back to the definition of limit point?
Yes. So a limit point, you mean of a sequence or of a sequence? Okay. So a limit point of a sequence is a point in the topological space such that there is a subsequence of that sequence, which for high enough members of the sequence, we always mean that for some n greater than capital N, intersects any open set that you give.
Okay, so the definition of a convergent point and the limit point, there are the 2 integers used for high enough. Are they related or independent?
No, they are related because the subsequence, for the subsequence, that point is a convergence point.
Yeah, so there should be like for the limit point, the integer of the members will be some n prime
Yeah.
greater than n of that.
Yeah. Of course.
And
What
then n.
exactly? When you select the subsequence,
Yeah.
then you relabel the subsequence with a new integer n,
Okay.
and then you say for large enough values of that integer.
Sure.
Because right, it doesn't matter whether you call your integer n or n squared or 2n or any other thing. So you can always relabel the subsequence such that n labels the element of that subsequence, and then
So we are like there is a point P,
Yeah.
which is convergence point.
Yes.
So there is an open set.
yes,
And in the open set, we have defined the open set like for an integer capital N.
Yeah.
There are some higher member than N. There are
all higher.
all higher members which are in there.
Yeah.
So when we define the limit point,
Yeah.
then we get a subset of here.
So the limit point of a given sequence is the statement that there exists a subsequence. I have to find that.
Yeah.
I'm allowed to find that, but I'm not allowed to put any new terms. Whatever is in that sequence, I can take out a subsequence how I like, but infinite one, and then that one should have that point as a convergence point.
So my main question is, if let there be a open set around limit point, and there is an open set about convergence point.
Yes.
Is the open set of limit point subset of that open set?
We don't ask that question. We simply the point is that first of all the open set is not given. It's for every open set I can find an n. Now we don't need to. So the definition is very clear.
Yeah.
First, you give me an open set around a point P. We are diagnosing if that point P is a convergence point or limit point. You give me an open set and you also give me a sequence. Now, if you want the convergence point, for your open set which you have given me, I'll show you that there's a capital N such that all high members of that sequence are inside. Then you say, no, I gave you a very big open set, I'm giving you a small open set, try again. I should be able to do it again. However many times you give me a new open set, however small you choose your open set, I will be able to find such a sequence. You may think you will defeat me by choosing the point itself, but that's not an open set. Now repeat the same thing for limit point. You will give me the sequence and you will give me the point. Then and you'll give me the point and you'll give me an open set. Now I will find a subsequence, relabel it, and then that subsequence for that this convergence point property will be satisfied. So in that way, convergence is a stronger requirement. A sequence which doesn't have any convergence point can still have limit points. And similarly, a sequence of curves which doesn't have a convergence curve might still have a limit curve, because in the limit curve I have first selected a subsequence to make the limit. Okay? Good. Okay. So now the lemma and then the theorem. So the lemma is that if x n mu of lambda is a sequence of inextendable. Up to now I never said anything about the curves except that they are smooth curves. Inextendable causal curves. Future inextendable, let's say. Future is just for definiteness. Causal curves. Having a limit point P then there exists a future, similarly future inextendable causal curve which is a convergence, which is a limit curve. Of the original sequence and passes through P. It's a bit long to write, but the short version is that if your sequence, which of course is future inextendable and causal, if it has a limit point, then it has a limit curve passing through that point. That's all we are saying. It's pretty strong. Just has one limit point, already guarantees the existence of a limit curve, and the existence is proved by showing how to construct that curve. And here, again, it's an ingenious use of usual limit point being extended to the concept of limit curve, and the proof goes like this. Here's my sequence of curves, and I'm given that it has a limit point P. Okay, so now I can pick a subsequence of my original sequence, and I know that it converges to P. Let me assume I've done that. Okay, so you gave me a sequence, but I picked a subsequence. Now what I've drawn here is my subsequence, so it converges. So P is actually a convergence point of my subsequence. Okay, now I'm going to extend P in order to make a curve such that every point on it will be a convergence point of my subsequence. And by definition, that means the result is a limit curve of your original sequence. It will be a convergence curve of my subsequence. It's this relation we've now discussed well. So the idea here is that you take this point P, you enclose it in a disk of some finite radius r, not disk but ball. Now here it's a bit tricky because a ball doesn't look like a ball in Minkowski signature. So we have to introduce a Riemannian metric, which is a Euclidean signature metric. In the neighborhood of this point P, and with respect to that metric, we'll make a ball of radius small r. Okay, that you can always do. And in this ball, we'll keep the boundary also. Okay, we include the boundary, so it's a solid ball of whatever, same dimension as the manifold. Okay, now, of course, you can distinguish the ball including its boundary from the ball without its boundary. If the ball didn't have its boundary, it would be an open ball. And because this is a limit point, or actually a convergence point of my subsequence, all the curves for large enough n will cut that ball. Okay, so that's step one. So this is a ball which I'll call VR. So all curves. So this is the subsequence. All curves in the subsequence will intersect VR. Okay. Now, because VR, I have given it a boundary, they'll pass through the boundary. You can't intersect a space without passing through its boundary. A ball, certainly. So they'll pass through its boundary, and here you can see the points where these curves are cutting the boundary. Now, this is a sequence of points in my manifold. In fact, on this ball, and the ball is closed. So this sequence should have a subsequence of points which converge to a point on the surface of the ball. Okay. Now it's with respect to our original sequence, this is a subsequence, but that doesn't matter. Okay. So the point where they intersect forms a sequence. And finally, that sequence has a further subsequence that converges on the ball. So this is because the ball is closed. Because it's closed. Okay. So in that way, by looking at that subsequence, I find a point here. Okay, and it's a new point, different from P, because it's a distance r away in this because of this ball, but it's also a convergence point, or it's actually also a limit point of the original sequence of curves. Okay, but it's only one point, and this is only one point. But I can repeat this procedure by shrinking r arbitrarily. And when I keep shrinking r, this point will keep coming closer. Or I could have started, so I take a kind of limit where I keep shrinking r and I get a line segment. And this line segment will have the property that it's a limit curve in its small region of the original family. Now, since this point here, I can call it P prime, is a limit point of this original sequence, I repeat the story. I draw a ball around this, I'll get another segment, and I can, the point is the size of this ball, you see, you may want to expand it till it covers the whole manifold, then you would be done in one go. But the manifold may have some weird topology, and this local Minkowski neighborhood of this point may only exist up to a finite amount. So you have to do it like that. So once you've got the next point, then you again make local Minkowski neighborhood, take next point, and keep repeating, and in the end you get the limit curve.
Can you explain again how this ball is defined?
Yeah, so the ball is defined by saying that given a point in a manifold M, this is always my arbitrary space-time manifold M, though it's taken to be globally hyperbolic, but we are not even using that now. You introduce an arbitrary Riemannian metric. So this idea actually, if you are trying to study relativity, is a little disturbing because we are doing GR where there's a given some Lorentzian signature metric. But you know, a differentiable manifold doesn't know about its metric. It's a new structure you put. If you can put a Lorentzian signature metric, you can also put a Euclidean signature metric. The reverse may not be true, but you can certainly put a Euclidean signature metric on any differentiable manifold, I think. Well, there may be some subtleties, but we hope they don't arise. And then in that metric, so you put a Riemannian metric and now you go to a neighborhood in which you can assume that the thing is approximately Minkowski. Okay, so now a ball is a well-defined thing. It's the locus of all points in that metric of constant distance from here. If we didn't take a Riemannian metric, then points which are very far away in coordinates could also be at small distance from here if they are along a null ray. But Riemannian metric doesn't have null rays.
So Riemannian just means that all with a positive
Yeah. Riemannian metric means the same as Euclidean signature. That's why I wrote this.
Only the signature is same, but the coefficients could be different, right?
Yeah, they're not. It's not necessary that it has to be exactly flat.
So the shape of the ball should that not depend on the choice?
Yeah, but it doesn't matter because we are talking a ball of some, a closed ball around a point is a well-defined concept in a metric space. So Riemannian metric makes it a metric space. And for any Riemannian metric, I can talk of a closed ball in some sufficiently small region. Yeah.
So alternatively, we have shown that if M is locally hyperbolic, it can be written as sigma times sigma cross R.
Yes.
And then we can just use the product topology to define balls.
The product topology to define balls, but that R is exactly what was the Lorentzian direction.
Yes.
So, yeah.
It still has open sets.
Yeah, of course, sigma cross R has open sets, but we have to put a metric on sigma cross R, which is not the metric of M. Because the metric of M has first of all, it's not a product metric. The topology is product, but the metric is not. But secondly, even if it was, it would be space-like on sigma and time-like on R. So we need a new metric, which is this Riemannian metric. And this keeps coming in for many, many different theorems in this field of causality and general relativity. The construction of a Riemannian metric as an auxiliary device to understand things. And in some way, it actually speaks to a problem we all have when studying relativity. We draw a line at 45 degrees and we say the paths along this line cover zero distance, but doesn't look like zero distance. Then we say we draw a normal to a null hypersurface, but the normal is in the null hypersurface. So our intuition just goes to hell. And sometimes we want to ask what is the vector pointing out of a null hypersurface. It's not the normal, it's something else. So when we introduce a Riemannian metric, at least we can satisfactorily define all these things in equations in that metric. Yes.
Couldn't we have, like, since this is a limit point, couldn't we have generally used open set in the topology, which would not require us to go in a neighborhood and use its closure? Because that closure will still contain the open set. In that way, like I was just asking,
Yeah.
if not, I think it, and I have not gone through that thing entirely, but it might not require us to even define a Riemannian metric or go to a coordinate patch.
So you want to go to an, but you see, if you don't define this, then what is the meaning of the size of the open ball? This is the problem. So let's just think of Minkowski space. It's a good question, but let's think of Minkowski space. What is the topology? How do we define topology in Minkowski space-time?
Yes.
We actually can't do it with the Minkowski metric, and we don't. We simply say, well, it's not yet Minkowski space-time. Just now it's Euclidean d-dimensional.
Yes.
So tensor product of R of n real lines, d real lines, and on that we put the Euclidean metric, just flat. Then we make a ball of radius r, and then we say all these balls which are point strictly less than the radius from the origin are the open sets. Okay, up to this point we never used Minkowski anything, but without doing all that we can't even define Minkowski space-time, let alone a general space-time.
That's like using the Rn basic open world topology of Rn, right?
Yeah, but the open ball topology of Rn, that's correct, but that's a metric topology. But a metric, for a metric topology, you first need to, so let's say this, a topology doesn't require a metric.
Yes.
You can define topologies without a metric, but pretty much in physics, the only sensible topologies we ever define are those which are metric topologies, which form a very well-loved, very intuitive and very nicely behaved subfamily of topologies. We can also define topologies where every set is open and closed and every point is both open and closed, and the topology exists and it's hard to see how you could ever do physics on it. So that's why we introduced the metric. What I'm emphasizing is that it's not the Minkowski metric which gives us the topology, it's the Euclidean metric, and once we have got the topology, we now pass to Minkowski's metric on that space, on that topological space.
That's the addition, like this metric, because I was thinking this metric that you're referring to is simply the Rn topologies, like Euclidean distance that we have, which is inherently always present in the Rn. Like if we have Rn,
exactly.
it will be an Euclidean.
Yeah.
That's how we define
That's
the
true,
open.
but it's not absolutely essential that this should be Euclidean, because you see there's a rule that in any manifold, at a point, up to first order deviation from that point, I can make the metric flat and its first variation 0. This is called Riemann normal coordinates.
Not referring to the metric actually, just the actual the dx comma y, the metric
that's the
defines the open ball.
That's right.
Not even the structure that we add
Exactly.
onto the manifold.
Exactly.
On our own.
Exactly. So that dxy is defining this ball.
So that's what.
Yeah.
Basically, we are using that dxy, which even comes before defining a metric in a sense, as a tensor. Like that, it comes before.
It
even
comes
defining
before
a
defining a Lorentzian metric to do gr.
It comes before even defining a metric tensor. So it's inherently
A
always-
Lorentzian metric, it includes it, but it comes after defining a Euclidean Riemannian metric. Without a Riemannian metric, the meaning of what is a ball doesn't exist.
But like, sorry to explain, but like when
no,
you
sure.
define a manifold,
Yeah.
you have said that there would be coordinate charts, and
Yes.
the coordinate charts will always be.
No, the coordinate charts don't come with any notion of distance, because you
right,
can't.
but they come when we say that there is a coordinate chart, we define that there is a homeomorphism.
Yes.
So for the homeomorphism to Rn, we require a topology on Rn, and that is generally the open world topology, right? On Rn, we for the homeomorphism.
That is true, but that doesn't. Okay, I mean that is true.
That open world topology inherently always
Yeah,
has
but
that
no,
identity.
but there's no. Okay, I mean that you're just telling me a way to find a metric on my
I'm
manifold.
saying that
But the
that
point is,
metric
it's highly non-unique. So I can pick. The statement here is I pick any. You can pick one. I can pick another Riemannian metric. You're saying that for a particular coordinate chart, you would be able to induce a particular metric on your
I'm saying that the
manifold.
coordinate chart already has, because
One coordinate chart has that, but one coordinate chart doesn't define a manifold. The
Yeah,
manifold
so-
is equivalence class of all compatible
We
coordinate
are
charts.
working patch by patch, right? Here, we are working here patch by patch, right?
That's true.
So,
But again, one coordinate chart will give you a open. I'm
it
saying
will
that
give-
it will give you a ball. What you're saying will work.
Yes.
But if somebody else uses a different coordinate chart, they won't land on the same ball. So therefore, it's not what you're saying is no different from saying we have introduced a Riemannian metric.
Okay.
You're just telling me one way to do it.
Because like
But it's
you
not
were-
a unique way. If it was a unique way, I would not have said introduce a
like,
Riemannian.
because you were saying something about that in a Lorentzian manifold going to a Riemannian metric is you were saying that there might be some complications.
No, I didn't say complication. I said it sounds like an odd thing to do suddenly in the middle of a discussion on Lorentzian geometry to stop and say no, but actually there's also a Euclidean signature metric. Okay, to me it sounds a bit arbitrary, like we stopped discussing Lorentzian signature metric just for this purpose. But the point is that it's the only way really to define sensible balls. And we need these balls to be both open balls as well as closable by adding their boundary. As open, they guarantee me that these curves cut them because that's the definition of limit point. And then by adding the boundary, I get a guarantee that those curves cut the boundary. Now I get a family of points. If I didn't have a family of points, I couldn't do the next step. And the next step is to say this family of points converges to a point as long as I'm allowed to pick a subfamily. This is the sequence of events. It's quite a number of events, but in the end we get this line segment, and if you're convinced of that, then you can repeat the process to get a finite line. But you can't have a Minkowski metric for a finite size ball in an arbitrary manifold. I mean, at least by choice of coordinates. You could introduce one. Probably the idea here is to introduce one which is Minkowski in a finite region. But you can't make that look Minkowski if it was already given in advance. Okay, very good. Yes, fine. So we proved this theorem that every family of future inextendable causal curves has a limit curve which passes through P, because we have shown you how to make that limit curve. Okay, and now we want to use this theorem to prove that CPQ is compact. Here's P, here's Q, and here's the space of curves like that, and we want to say it's compact. And we do this as follows. So first let's assume, now of course this is true only in a globally hyperbolic space, so this is, we must insist. Where globally hyperbolic means there's a Cauchy surface, so I'm drawing the Cauchy surface and I'll use its existence to prove this. Okay, so I've taken P and Q in the past of that Cauchy hypersurface, with Q being to the future of P, just to be definite. And we take an infinite family of causal curves. And again, we want to show that CPQ is compact, so the infinite family of curves between P and Q, so any infinite sequence of causal curves from P to Q has a subfamily that converges to a limit curve also from P to Q, because I'm only considering curves from P to Q. So this is the restatement of the theorem about compactness of CPQ. This is the sequential compactness of CPQ, and second countability we already said is simple. So this is the only extra thing we need to add. Okay. Now the trick is to play around a little bit with these points P and Q. So first of all, P, so the steps in the proof. 1, P is clearly a limit point of the whole sequence. Very trivially, because the whole sequence passes through P, so obviously it's a limit point. You don't have to check anything. Okay, it's a convergence point in fact, even better. of the whole sequence. Okay. Now let's take any sequence. Yeah. So P is a convergence point, as I said. Now let us remove Q. So we have this family and they all end at Q, and delete Q from it. So we first delete it and later we'll put it back. Okay. Then these curves x and mu of lambda become future inextendable. We had a discussion on inextendability of curves, and if curves are trying to end at a point and if that point isn't there, then they aren't extendable. Okay? Because the intuition is, how would you extend it? You could only extend it by going around the point, since the point is not there. But they are all coming arbitrarily close to the point. This point is like the end point of an open interval for them. So once they have come, so the further you go on the curve, the closer you get to that point without ever reaching it. But if that point is not there, then what can you do? There's no way to extend this curve to get around it. Okay. So they are inextendable. Now we can use the previous dilemma, which says that we have a inextendable curve through P up to Q, which is missing, which is the convergence curve of a subsequence. The lemma was, which we did for the last 10-15 minutes, was to show that whenever you have a family of future inextendable curves, causal curves, all are causal, then if there's one limit point, then there's a limit curve. So it's actual, and it's the okay. Instead of calling it convergence curve of subsequence, I'll just call it limit curve of the sequence. These two terms are interchangeable. Okay, so there's a limit curve. So we've got the limit curve and we are almost done. Now we put back the point. And we ask, what is this limit curve going to do after we put back the point? Remember, we only know this is a limit curve and that it passes through P. We don't actually know what it does near Q. It's just a limit curve. Okay. Now, when we put back Q, it has two choices. Either it remains inextendable, that means it approaches Q arbitrarily close but doesn't touch it, or it actually touches Q. Okay. Now the limit curve can do two things. Remains inextendable. Okay. Then we put back Q. Remains inextendable, or terminates at Q. If it terminates at Q, we are done. We have shown that all the curves from this family from P to Q has a limit curve from P to Q, which is in the same space CPQ. So the space is compact. So this is the good one. This is the bad one. It remains future inextendable. Now look at this limit curve. Remember, there is a Cauchy sequence sitting, Cauchy hypersurface sitting there, and here is a yellow curve which is future inextendable. So it can't pass through the Cauchy hypersurface. Then the manifold isn't globally hyperbolic. In this case, contradicts global hyperbolicity. So it's a very subtle little thing, but you see, this shows that if you assume the global hyperbolicity as defined through Cauchy hypersurface, then CPQ is compact. Now, one would have to prove the reverse also. Supposing I assume CPQ is compact, That means I have, for every family of sequences, there's a subsequence which actually has a limit curve. Then I have to show that every curve in the manifold passes through a Cauchy hypersurface. So I'm going to skip that, but that is discussed involved. So we have only proved one direction. You can look it up, and if you want to talk about it later, please bring it up. Okay, now everything gets easier once we are done with this. So this proves CPQ is compact, and if you have followed up to this point, then you are 7 out of maybe few dozen people in the world who know that CPQ, why CPQ is compact. So something to be very happy about. Okay. It might be interesting for any of you to try and track down Léray's original manuscript of his lectures at Princeton, where he actually gave this as a kind of definition of globally hyperbolic system in some context of solving some differential equations on manifolds. I haven't done that. Okay, corollaries are very interesting but also quite simple. I don't know why I suddenly went to yellow chalk, but on this board it seems to look better actually. So one, which I don't think I need to prove, CKQ is also compact, where K is not a point but a compact subset. So I can consider the family of curves that start on a compact subset K and terminate at Q, which obviously has to be in the causal future. So curves like this, they don't have to start from the same point. They just have to start from K. Alright? Then the claim is that any infinite sequence of such curves has a limit curve, as long as these are causal and causal curves, has a limit curve which also starts somewhere on K, again not specified, but terminates on Q. This is actually the version which will be used, so it's nice that we sort of got it for free. This is the one which applies in black hole physics, okay, for the singularity theorems. So we probably don't actually need CPQ being compact, but it's almost obvious that if CPQ is compact, then so is this. We have to be a little careful because now all the curves in the family can start wherever they like, and the limit curve can start at yet another place, which is in the place where any of these starts. So, but there are a lot of theorems like this where we can extend theorems of curves between 2 points to theorems relating to surfaces. In fact, when we discuss focusing, geodesics and focusing, we'll actually encounter this situation. Okay. Now we can come to the last definition, which is actually very nice. The last definition was that dpq is compact, j plus of p intersection j minus of q is compact. This is another corollary of what we just proved. And as I mentioned at the beginning, this is the third independent definition of globally hyperbolic, and it's the one that the textbook of Hawking and Ellis uses. Okay, again there are two directions to prove. What I'll prove is that if CPQ is compact, then this thing is compact, and the other direction you can look up. Okay, so let's first of all draw dpq. So here's P, here's Q, and P has its J plus, Q has its J minus, and so this thing is dpq. The causal diamond, as it's called, of the points P and Q. Now one thing very obvious is that all the curves in CPQ have to fit inside this. We have already studied the family of causal curves from P to Q and shown that that family is compact, but in particular they have no choice to go outside, and I think I might have said this once before. If it strays out here, then it has to somehow make it to Q in a space-like way. So that's not good. If it strays out here, it's already space-like. So it just can't stray out anywhere. At any point, if it tries to jump out of this, it can certainly go out, but then it can never reach Q. So this is a nice time-like curve which has gone out of the causal diamond, but it has lost all chance of reaching Q while remaining causal. So CPQ is, the curves in CPQ are all inside here. So that's the first observation. Okay. Now we want to show this space is compact, and again we use sequential compactness, sort of third time. So because second countability is always guaranteed for this situation. So we want a sequence of points Rn, where let's say this is R1, R2, R3, R4, and we want to show that there exists a subsequence of any such sequence which converges to a point which still lies inside this causal diamond. Okay, and you can almost guess what's going to happen now. We can simply construct a family of curves such which are causal, and each one of them passes through one of the points in my infinite sequence. I'll just draw this infinite sequence. Since the sequence is fully inside dpq, there are definitely causal curves from P to Q which pass through it. Okay. Now I'll use, unfortunately now I'm paying for using white chalk. Now I'll use the compactness of CPQ, which says that there is one curve which is a limit curve of that. That means there's a subsequence of these curves which converges to a convergence curve here. Okay, but that subsequence defines a subsequence of these original points. I simply pick only those points in my original sequence, which is a subset of those such that the curves in the subsequence pass through them. Okay, and now there's a last thing to show. Yeah, exactly. Now the last thing is to observe that this curve itself is a compact set, because it starts at P and ends at Q, so it's a compact set, and that is enough to argue that there is a point R on this convergence curve such that the Rn's all converge to it. And since the whole convergence curve, white curve, is fully inside this domain, obviously any point R which you find on it has to be inside the domain, and therefore the domain is compact. So this is the proof of this theorem. Again, I will send you notes. So now today I'm finishing the chapter on causality, and you will get the causality notes. Okay, and everything is done there. And some things which are not done at all in my notes, I refer to Wald for that, or to Witten, or to some other reference. Okay. The exercise for you is to look at the converse theorems. For example, compactness of CPQ or of dpq should imply the existence of a Cauchy surface. That's the converse direction, the one which we didn't do. So those are very good exercises to get a handle on these things. Okay. There's also a small corollary of this. So it turns out in a Hausdorff space, if something is compact, then it's also closed. So this is a theorem in Wald's book, theorem 8.2. So closed. This is something familiar in ordinary multivariable calculus, because actually in multivariable calculus, compact is defined as being closed and bounded. So in particular, if something is compact, it's closed. We are not in multivariable calculus literally, because we are in a arbitrary differentiable manifold, though globally hyperbolic. And but all we need is the fact that that manifold has this Hausdorff property, which I hope you have looked up, but it's nothing more then saying that if I have 2 points P and Q, then I should be able to find open sets which enclose P and Q, which are completely disjoint from each other. Any 2 points P and Q in a Hausdorff manifold can be, I should have said this long ago, obviously. It is again in my notes. It just says that it is called a separability property. It's a topological property that for any 2 points P and Q in my topological space, no matter how close they may be in a metric sense or any sense, there's always an open set surrounding each one, such that the whole open set and this open set are disjoint. So that's always manifold space-times are always Hausdorff. I may have said it when I introduced the definition of space-time. Okay, now 2 more corollaries and we can actually stop. One is almost trivial if you accept a rough hand-waving argument. Another corollary, J plus of P in a globally, this is always in a globally hyperbolic space-time. J plus of P is closed. Notice how much time it took for us to get here. In general, I plus of P is open, that we said from day one when we defined I plus, the chronological future. We never made a statement what is J plus, open, closed, both, neither, what is it? Well, it turns out it is closed only in a globally hyperbolic spacetime, otherwise it need not be.
So in this case, the converse is true. So DPQ being compact implies that the manifold is globally
Yes,
hyperbolic.
yes, that's what you have to. Globally hyperbolic as per the definition of Cauchy hypersurface. Yeah, that's what I said was left as an exercise to think about. Both DPQ, you can either start with DPQ being compact or CPQ being compact. Both ways you should be able to argue that there is a Cauchy surface. Okay, and now the proof of this one should, there's an obvious, can you think of an obvious way to get it from this? Come on, we are trying to prove that J plus of P is closed, and we have already proved that the causal diamond PQ, yeah, take Q to infinity. That's the verbal proof. There's a little more precise proof. So informal proof. The formal proof is not much more difficult. What we basically do is, since there isn't a Q in this problem, we put a Q into the problem and then we cycle this. If you like, I can do it. I might as well do it now just for completeness. So suppose J, okay, so formal. Suppose J plus, so suppose the contrary, not closed. Okay. Then we should reach a contradiction. So that means that there is a point Q which lies in the closure of J plus P, but not in J plus P. Right? That's what it means to say that J plus P is not closed. So let's draw it. Here's P, here's J plus of P, and here's a point Q. I don't know how to draw it any better. It's supposed to somehow be in the closure of J plus P, but not in J plus P itself. Maybe I should draw it slightly out. I don't know how to say it. It's in the closure. That means it's arbitrarily close to J plus P, but not in it. And that's the statement that J plus P is not closed. Okay. Now let's call this point. Let's call this point P prime. Okay, now let's choose a point Q in the future of this point. So this point has its light cone, and let's choose a point Q here. Okay. Now let's draw J minus of Q. That's J minus of Q. The causal past. Okay. So obviously P prime is in it, as you can see. Okay. So P prime is in J minus of Q, but not in J plus of P. Okay. So P prime cannot be in the intersection of these two. If it's not in both of them, it's not in the intersection. But what is this intersection? It has a simpler name. This is dpq. So P prime isn't in dpq. However, as we saw, P prime is in J plus of P closure. And of course, it's also in the closure of J minus of P because it's already in J minus of Q because it's already in J minus of Q. So obviously, it's in its closure. So therefore, it's in the intersection of these, which is the same as the closure of the intersection. And this is the closure of dpq. So we found that P prime is not in dpq, but it is in the closure. This contradicts the fact that dpq is closed. Closed. The contradiction. So dpq is closed. So we proved the result that J plus of P is closed. And there's now the very last theorem, and it's also quite simple, and it's the end of our discussion on causality. And it's in some way, if you have really hated the last few lectures, you would probably wish that I just gave this statement without proof, because it's one of the most important things we'll need. Now it's trivial to prove because of everything we've done. So I hope you're used to these abbreviations. Globally hyperbolic spacetime. There is a unique geodesic which maximizes proper time between P and Q. Of course, assuming dpq is non-empty. Otherwise, there's nothing between them. There's no time like anything between. Yeah. Okay. So this proof also follows from compactness of CPQ. So we are getting some benefits from that theorem that we very painfully proved. And the way it follows is that we can try to violate this. We basically just need to show that there's a maximum allowed proper time. You see, if we can show there's a maximum proper time, it's going to be there's a unique curve of maximum proper time, it's going to be a geodesic. Because geodesics make the proper time stationary. Okay. So what we do is, we make a family of curves of increasing, so suppose we make a family of curves of increasing proper time. So we try to violate this.
Is it
Maximum. Proper time is maximized. So geodesics in space, they minimize the distance, but in space-time, they maximize the proper time if they are time-like. One problem is that null geodesics don't do anything to the proper time, which is 0, and it's a nightmare absolutely, and we are going to face that interesting nightmare quite soon, just after our discussion of black holes. But anyway, so good. So proper time tau n. Now let's suppose that this tends to an arbitrarily large, that is, it has no limit. Suppose this sequence has no limit. And it doesn't even have a limit point. So that means that the only way that can happen, so this is curves of increasing proper time. So we choose the sequence such that every tau n is greater than the previous one. And now let's suppose that it has no limit point. Then that means that for large n, there is no tau to which this converges, nor even a subsequence converges. Okay, but this contradicts the fact that the curves have to converge to a limit curve. This we know from compactness of CPQ. Okay, so let's assume our curves xn, x1, x2, x3 are labeled by their proper time tau 1, tau 2, tau 3. We know that this sequence of curves at least has a subsequence which converges to the yellow thing. And the yellow thing is a fixed curve between P and Q, and therefore it has a fixed proper time, which is not infinite. Okay, and you can also understand intuitively why it can't be infinite, because to get infinite proper time, it would have to run around. It can't be a causal curve anymore. And it's because it's stuck inside that dpq. Okay, so therefore there is an upper bound. So this is a contradiction with compactness of CPQ. So see how the theorem we proved enters in a very crucial way into this result. So therefore there must be an upper bound on the proper time. So let me write it here. Therefore there exists a maximum proper time for, let's call it tau bar, and we are done. There's a curve of maximum proper time. And now you can just, yeah, so now,
This curve does it not depend on the choice of family of curves that we choose?
maybe. So we choose a, that's right. Oh, I see. Oh, good. You're saying that I've taken an arbitrary family. Yes. I think I have to, sorry, I skipped a sentence. Now I take the, there exists a max proper time for this family. Thank you, Sonal, that is very useful. I had. Now find the minimum of this maximum proper time over all families. So nobody is really seriously saying that you can do it, but in principle it's well defined. Okay, so you find the least upper bound taken over all families of curves, and now pick a sequence of curves which actually converge to that proper time. Okay, then by compactness this has a convergent subsequence which converges to a curve with that proper time, and that curve is the limiting path, and because of compactness it has there's a definite path and it has a definite proper time, and you can't go above that. So this is the last part of the proof. Exactly. So one family of curves would not have been enough. We find upper bounds on tau bar from every family of curves, then we take the lowest one, and that's the proper time maximizing geodesic. So theorem is proved and causality chapter is over. Questions? Okay, thank you.